Okay. Anyway, so next, what is version space search? What is version space search? So in this method, first we want to create a version space of the problem, and that is the first thing we want to do. Okay. Okay. First we want to define, I cannot have a version space or concept space. So what is a version space? Okay. Version space of the concept to be learned is created. This is the first step. First step, we want to create the version space. Okay. Then a search, on this concept space is performed to find a concept or solution that is consistent with the training examples. Okay. That is consistent with all training examples. With all training examples. So this is the basic concept of version space search. First, we want to create a version space of the problem. Then we want to apply a search method. Here, which are the different methods? Here, which are the different search methods available? Which are the search methods? I told this one, specific to general, general to specific, and candidate elimination algorithm. Okay, these are the different methods. Okay. Okay. Then next, example of version space. Okay. First, we want to familiarize with what is version space. Okay. For example, consider an object. Consider an object, and we are considering this. An object. Consider an object, and an object having the properties of size, color, and shape. These are the three properties of the object. Then also it takes the values. For example, the size attribute takes the value. These are the values taken by the size attribute. It can be large or values. Size attribute will take the value large comma small. Color will take the value red, white, blue. Okay, and shape will take the value ball, brick, cube. So this an object is basically defined in this way. Okay? An object is defined in this way. So an object is properties. Okay, so we define an object. Then for this object, we want to create the version space. To create the version space, and we want to create the version space. Okay. In order to create the version space, we can use this generalization operation. Okay. We want to create the version space of the problem. For that, we can use various generalization operations. Okay. So, let's see. Here. So we want to create, this is the version space. Okay, you cannot hear. This is the version space of the problem. This is the version space. this is the version space. Okay? This is the version space for creating this version space. Okay, for creating this version space, we can use various operations or operators. Okay, okay, we can various operators. Which are the different operators that we can use? We can these operators. Okay, that operators are called generalization operators. Okay, generalization operator. This is the university question. Which are the different generalization operators for and that can be used for creating the version space? Okay, so this is the version space of the problem. This is the version space of the problem, and for creating the version space we can use various session operations. Okay, so which are the generalization operations? Replacing constant with the variable. Okay, this is one generalization operation. For example, suppose this is a solution or hypothesis. Okay, this is a solution or hypothesis. We can replace the constant value bold with the corresponding variable x. Okay, then this is one operation. Okay, this is the first operation. Next is dropping condition from a conjunctive expression. Okay, so there are different hypotheses. Okay, or these are called hypotheses. Okay, this is one hypothesis. This all termed hypothesis. So can use conjunctive operation to combine this hypothesis. So here the second rule saying second operation is dropping condition from a conjunctive expression. We can drop a conjunction. That is the second operation. That is also simple. Next one is adjunct to an operand. Okay, next one is adding a disjunct. Disjunct means means union. Okay, we can union operation to the expression. Okay, for example, you can note here this is the union operation. That is the third one, and the fourth one is replacing a property with its parents in a class hierarchy. Okay, another fourth one is replacing a property. Okay, replacing a property with the property means attribute value. Property with its parent in a hierarchy, with a parent in a class hierarchy. For example, if we know that primary color is a superclass of red, then you can note here. Okay, suppose color x comma red is there, then we know that red is a primary color. And if you can know, this is an example, this is just an example. If we know that primary color is a super red, then we can replace red with the primary color. Here primary color is a super class of red, then we can use operator. Okay, what is more general operator? For example, P greater than Q or equal to Q. There will be G. Anyway, suppose this is the what is its meaning in the version space problem? P greater than or equal to Q means that more general than Q. Okay. For example, this is an important concept. It's more general. What is the meaning of more general? Okay. For example, suppose this case. Suppose consider this. We want to prove this. We can note here color of x comma red greater than or equal to color of ball comma red. Which one is more general? in this. Here, the question is, which one is more general in this expression? There are two hypotheses. This is a very important topic. We want to apply this concept in the algorithm. So my question is, which is the more general concept? Okay, that is color of X comma red or color of ball comma red. Here, this first one, okay, here, this first one contains a variable X. Okay, it contains a variable. So it is more general than this. Here, there is no variables. Okay, so try to understand that concept. What is the more general? Okay, here color of X comma red. X is a variable. Okay, at the same time here color of ball comma red. Ball and red are values and ball value of the variable X. In this situation, color red is more general than color of ball comma red. Okay, this is a very important concept. What is the meaning of more general? What is the meaning of more general? So this is another operator. Anyway, we will familiarize with concept while discussing the algorithms. Okay. Next, another point is P covers Q. If a concept is more general than concept Q, then we say that P covers. Then we say that P covers Q. Then we say that P covers Q. That then we say that P covers Q. Okay, P covers Q. Anyway, and this is about the different operations used in the version space search. By using these operations, this concept space, this is the concept space, and this is the concept space. Okay, this is the concept space. This concept space is by using this operation, these operations. Okay, you can note here. This is the topmost hypothesis, and the topmost hypothesis is the most general hypothesis. Okay, try to understand this concept also. What is most general hypothesis means? This is the topmost hypothesis or concept which contains all variables. Okay, which contains variables only. Then this is the most general hypothesis in subspace. Okay, then another concept is, which is the most specific hypothesis? Most specific hypothesis in this. I'm defining two terms. Most general hypothesis. Most general hypothesis I defined. Which is the most specific hypothesis? This one. Okay. You can note here. This is the bottommost hypothesis. The bottommost hypothesis is called most specific hypothesis. It contains no variables. Okay, it contains no variables. So the uppermost hypothesis or the topmost hypothesis is most general hypothesis, and the bottommost hypothesis are called most specific hypothesis. Okay, you can note here, these are all different, uh, these are all different most specific hypothesis. The most specific hypothesis consists only the values. It contains no variables. Okay, try to understand that what is most general hypothesis and what is most specific hypothesis. Okay, what is most general hypothesis and what is most specific hypothesis. So I told this is the most general hypothesis in the version space, and these are the most specific hypothesis in the version space, and within it, it contains a lot of hypotheses. Okay, in between the most general and most specific hypothesis contains different hypotheses that constitute the version space. Okay, so what is space? Try to understand this concept. Okay, so what is space means, and the hypothesis between most general hypothesis, most specific hypothesis is called the version space, and all called the concept space. Okay, so what is concept space? Concept, it includes the most general hypothesis and most specific than all other hypotheses, and this is called the concept space. Okay, so basically, in order to find a solution, what we will do, version space search, search this space. Okay, in the space search approach, in order to find a solution, there are two approaches. One is search from this direction to, that is top to bottom. Okay, search from top to bottom, that is one approach, and another is search from top to bottom, bottom to top. There are two. One is search from, one approach is search from most general hypothesis to most specific, and another approach is search from most specific hypothesis to most general, and another approach, a combination of these two. Okay, so these are the approaches, and based on that concept, three algorithms are developed: specific to general search, general to specific, and candidate elimination algorithm. What is candidate elimination algorithm? Candidate elimination algorithm is a combination of both searches. Anyway, next we are moving to the first algorithm. Okay, so there are, as I told, there are three types of algorithm. One is specific to general search, general to specific search, then candidate elimination algorithm. It is a combination of. So next we want to discuss the some points about it. General to specific search algorithm, general to specific search algorithm and specific to general search algorithm reduce the version space. Okay, it always reduce the version space in a general to specific direction and specific to direction. Okay, so what is general to specific direction? You can remember this diagram. Okay, general to specific, bottom to top. Specific to general means top to bottom. So these two algorithms reduces the version space in that way. Okay. Okay, general to specific search algorithm and specific to general search algorithm reduce the version space in a general to specific direction and specific to general direction respectively. Next point, these algorithms are data driven algorithm. These algorithms are called data-driven algorithms. And another is, these two algorithms are basically supervised learning algorithm. In the machine learning, studied various algorithms. For example, which are the different supervised learning algorithms you studied in the previous semester S7, which includes a decision neural network and SVM, support vector machine, etc. These version space search algorithms are also supervised learning algorithms. This is also another point about the version space search algorithm. Anyway, now we are moving to discuss the first algorithm, general to specific search algorithm. Okay. So we are going to discuss about the general to specific search algorithm. Okay. So this is the algorithm for general to specific search. Okay. This is the algorithm for general to specific search. In the examination, I think they asked one question directly from this. Explain general to specific search algorithm. And this is the problem related to this algorithm. Okay. We want to discuss both. Okay. How it works. We want to study how this algorithm works based on this example. Based on this example, we want to discuss the working of general to specific search algorithm. Okay. Anyway, next, this is the algorithm. As I told, what is general to specific search algorithm? General to specific. General to specific. So, what will be the direction? General means topmost. Topmost, top to bottom search. This is basically a top to bottom search method, because general to specific searches. Okay. So you can remember this. You can note this. Okay. This is the concept space. We will search from the most general hypothesis to the top bottom. Most hypothesis to find a solution. Sometimes we may get a solution between the search. Okay. So that is the approach. And then next, so this is the algorithm. And so this, in the first step, we can go to the algorithm and parallelly we can discuss this example. Okay, that will be simple. Anyway, first, initialize G. So this is the first step. Initialize G to contain the most general concept in the space. Okay, so in the first step, this is basically the initialization step. These two steps are initialization steps. Okay, these two steps are initialization steps. And in that first step, initialize G to contain the most general hypothesis. So my question is, what is most general hypothesis? Most general concept in the space. Okay. For example, we are considering this. Okay. This version space we are considering. Okay. This is the version. Suppose this is the version space of the problem, and this is the most general hypothesis. This is the versions problem, and this is the most general hypothesis. So, 1 minute. Okay, so we want to initialize G to contain the most general hypothesis. Next, another variable is P. Another variable is P. P contain all positive examples seen so far. Okay, so initially P is empty. Okay, initially P is empty. So we defined two variables, one is G and another is P, and P is initially empty. Okay, P contains all positive examples seen so far. So try to understand the two variables G and G means general hypothesis set. Okay, G is a variable to denote the general hypothesis set, and initially G is fixed with G is contain most general concept in the space of that problem. Okay, so this is the space of our problem, and initially we G contain this. Okay, initially G contain this. Anyway, so next we want to do two procedure. One is for the negative instance. Okay, if a negative instance is given, then the algorithm will do this task. Okay, this task. We can discuss that later. Okay, similarly, if a positive instance is given, we want to do this task. We want to this is the organization of this algorithm, and now we are going to discuss an example. Okay, so as I told you, initially G contains, this is the search from most general to most specific. So G initially contains the most general hypothesis in the version space, which is the most general one, which is object of x comma y comma z. Why it is in this way? Object x y z. Why it is in this way? Because you cannot hear. This is the version space tree, and this is the topmost or most general hypothesis. It contains all variables only. Okay, it contains the variables only. Okay, you cannot hear. It contains only the variables. Okay, x y z. Okay, that is called the most general hypothesis, and initially this is the most general hypothesis. Now you can note a negative example is given to the algorithm. Okay, now you are giving a negative example. Okay, there I told this is a supervised learning algorithm. So there are positive and negative examples will be there. There are two class of examples. You can just refresh the S7 class. This is a supervised learning class, and there are two classes. One is negative class and another is positive class. So first I am giving a negative example to the algorithm. Then what the algorithm will do? Okay, so initially G is equal to 1 minute. Initially G G is the most general. What about P? There are two variables G and P. What is P? So what is P? P is another variable. What is P? What is P here? Initially, what is the value of P? P is the set of positive example so far we have seen. So we didn't see any positive example. So P is initially empty. Okay. P is initially empty. Okay. This is the situation. G contains the most general hypothesis and P is initially empty. At that time, a negative example is coming. Okay. So what we will do, what the algorithm will do, it will process this part. It is a negative instance. So the negative, since it is a negative instance, it will execute this path. Okay. Sorry, it will execute this code. Okay. So this is very important. It will execute this code, and okay. So what is the first step in this code? For each G, it's very important. Just note it. For each G belongs to G that matches N. Okay. First saying the G is a set of hypotheses. Okay, G is a set of hypotheses. G is a set of hypotheses. Okay. Initially, G contains the most general hypothesis. If that hypothesis matches with the negative example. Okay, then replace G with its most general specialization. Most general specialization that do not match N. This is a complicated sentence. We want to analyze what it actually means. Okay, what it actually means. This is the first part of this algorithm. Okay, first part. It's saying for each G belongs to G that matches N, replace G with its most general specialization that do not match N. This is the first part. Then we want to execute. After performing this, we want to execute delete steps. There are two delete steps. This is delete. Uh, there are two delete steps in it. Okay, there are two delete steps. Which are the delete step? This is one delete step, and this is another delete step. Okay. This is another delete step. So we want to first execute this part for loop, then we want to execute two delete step. Okay. So what is this meaning is that now we are going to the example. Okay. So initially this is G. G is object of x comma y comma z. Okay. It is a most general hypothesis, and if and a negative, this is a negative example. This is the negative example. This if the negative example matched with this one, if the negative example is matched with this one, if the negative example matches with this hypothesis, then we want to do something. Okay, so whether it match or not, that is the question. Okay, here object of x comma y comma z, negative is small red brick. Okay, so this is the most general expression. Okay, which value x can take? X can take the value small. Okay, y can take the value red, z can take the value brick. Okay, so it matches. Okay, this is a negative example. We want to check whether it match with G. Okay, this is a negative example. We want to check whether the negative example match with G or not. The approach should be take this one. Then x can take which values? Small, large, etc. So x can take small. Y can take red value. Z can take brick value. Because all are variables here. Okay. So here correct values are given. Okay. So these three are matched with this. So we will execute the for loop. This part we will execute. So that we can discuss in the next class. Okay. Okay. That we can discuss in the next class. Okay, please give the attendance in the chat box. Okay. Okay. Then, okay, thank you.